Hi guys, my name is Mohit Best and I'm here to discuss about my microcontroller IC MSP430G2403 by Texas Instruments. So here's the block diagram of my IC, which consists of RAM with 256 bytes, CPU with 16 megahertz of frequency including 16 registers, um, ports with interrupt capability, pull up and pull down registers. It has two timers, timer 0 and timer 1 with 3cc registers. So here's the block diagram of my CPU. It has 16 registers with 12 general purpose register and a program counter, stack pointer, status register and constant generator. So this is the frame controller of my microcontroller, which consists of cache and interconnects command using control register. So to discuss, the next topic is instruction set of the microprocessing element with clock cycle required, memory required, flex affected, type of instruction based on addressing modes, operations, etc. So there are three formats used to encode the instruction for processing by CPU core: double operand, single operand, and jumps. The instructions for double and single operands depends on the suffix word .w or .b. These suffixes allow word or byte data access. If the suffix is ignored, the instruction processes word data by default. The clock system is supported by the basic clock module that includes support from a 32,768 Hz Watts crystal oscillator and internal very low power low frequency oscillator, and an internal digitally controlled oscillator called DCO. The basic clock module is designed to meet the requirements of both low system cost and low power consumption. So here are some instructions with their cycles of instructions fetch of the cycles fetched by the operands and the total cycle required. So our next topic is microprocessing element architecture. The MSP430 CPU has a 16-bit RISC architecture that is highly transparent to the application. All operations other than program flow instructions are programmed as register operations in conjunction with 7 addressing modes for source operand and 4 addressing modes for destination operand. The CPU is integrated with 16 registers that provide reduced instruction execution time. The register to register operation execution time is 1 cycle of the CPU clock. 4 of the registers R0 to R3 are dedicated as program counter, stack pointer, status register, and constant generator respectively. So here we are now to correlate the microprocessing element architecture with the architectures discussed in module 1 and 2. So the MSP430 von Neumann engineering has one location space imparted to uncommon capacity registers, fringe control registers, RAM, streak ROM memory. Right now there are two viable CPUs existing inside the MSP430 microcontroller family. The program controller includes 20-bit program counter points to the next instruction to be executed. Each instruction uses an even number of bytes, 2, 4, 6 or 8 bytes, and the program counter is incremented accordingly. Multiply and accumulate (MAC). These registers store the after effects of duplicate task and increases and accumulate activities. On the off chance that the overcome is to be utilized for one other than duplicate what's more aggregate activity, it must be moved to an overall register. And the next one is program procedure register. This register stores the return address from a subroutine method. It stores the return address in the strategy register when a subroutine is called. Hence, There is no memory access in a subroutine call and no guidance pipeline slowdown. So next topic is register organization. The MSP430 CPU has 16 registers. Large 16-bit register file eliminates a single accumulator bottleneck. High bandwidth 16-bit data and address bus. R0, which is program counter. This register always points to the next instructions to be fetched, as I have already discussed. R1, which is known as stack pointer. The MSP430 CPU stores the return address of routines or interrupts on the stack. User programs store local data on the stack. R2, which is status register. The status of the MSP430 CPU is defined by a set of bits contained in register R2. R2 and R3 constant generators. 6 different constants commonly used in programming can be generated using the registers R2 and R3 without adding a 16-bit extension word of code to the instruction. R4 to R15 are general purpose registers. These registers can be used as data registers, data pointers, and indices. They can be accessed either as a byte or as a word. So the next topic is algorithms used for signed and unsigned calculations. Uh, some operands like some algorithms like add is used to add source to destination. Add C is used to add source and carry to destination. Sub C subtract source from destination with carry, and subtract source from destination. Multiplication and division in the absence of hardware multiplier require many instruction cycles, especially in C. This report discusses a method that does not need a hardware multiplier and can perform multiplication and division with only shift and add instructions. The method described in this application report is based on Horner's method. The MSP430 microcontroller CPU can perform a register shift or add in one instruction cycle. This allows fast execution of multiplications and divisions using Horner's method. This method not only produces accurate results but also provides a very good dynamic range, as it does not totally depend on finite word length effects like some of the conventional methods. So our next topic is control logic system and the correlation between its performance and the type of control units used in module 3 of our COA syllabus. So flags, first of all, flags are required to determine the outcome of the preceding ALU operation and the exact status of the processor. Control signals from the control bus. The control bus generates control signals such as acknowledgement and interrupt signals, which are sent to the control unit. The clock system is supported by the basic clock module that includes support from a Watts crystal oscillator, an internal very low power frequency oscillator, and an internally digitally controlled oscillator. So next topic is explain the memory management in the processing element selected. Let's list its addressing capabilities, memory mapping techniques followed. Find the advantage of memory design and management techniques over the concepts given in module 4 and COA syllabus. Devices with a memory configuration of 64 KB or less uses the small memory model with basic address range of lowest 64 KB and do not care about code segments and data pages. The data bus is 16-bit or 8-bit wide. For those modules that can be accessed by word data, the width is always 16 bits, and for the other modules is 8 bits. They should only be accessed with byte instructions. The program memory and the data memory can be accessed with byte or word instructions. Part of peripherals modules are realized as 16-bit wide or 8-bit wide modules. Data in the memory. Bytes are located at even or odd addresses. Words are located in the ascending memory locations aligned to even addresses. The low byte is at the even addresses followed by the high byte at the next odd addresses. In internal ROM organization, we have various sizes of ROM up to 64K bytes are possible. The common address space is shared with special function registers, peripheral module registers, data and code memory. These special function registers and peripheral modules are mapped into the address range starting from 0 up to 01FF hexa. RAM and peripheral organization. The entire RAM can be accessed in byte or word data using the appropriate instruction suffix. The peripheral modules are located in two different address space. The special function registers are byte oriented by hardware. The peripheral modules are byte oriented by hardware and mapped into the address space from 010H to 0FFH, and peripheral modules that are word oriented by hardware and mapped into the address space from 100H up to 01FFH. Peripheral modules uses address allocation. All peripheral modules are accessed, assessed, and controlled by the software. All instructions are approved for the data interchange operation. Next is the flash memory. The flash memory can be programmed through the SPI-B wire, JTAG port, or in system by the CPU. The CPU can perform single byte or single word writes to the flash memory. Features of the flash memory includes flash memory has n segments of memory main memory and 4 segments of information memory. Each segment is in main memory is 512 bytes in size. So next question is elaborate the pipeline and parallel processing capabilities of the unit and hazard management technique. So first of all, the IC does not have pipelining, parallel processing to permit equal handling of the CRC. The direct input move register usefulness is actualized with the XOR tree. This usage shows the indistinguishable conduct as the LFSR approach after 8 pieces of information are removed in when the LSB is moved in first. The age of a mark count must be begun by composing a seed of the register to introduce the register. Next comes the hazard management. There are circumstances called hazards that forestall the following guidance in the guidance stream from being executing during its assigned clock cycle. First is structural hazard. They emerge from asset clashes when the equipment can't uphold all potential bands of guidelines in concurrent covered execution. Second is data hazards. They emerges when a guidance relies upon the after effect of a past guidance in a manner that is uncovered by the covering of directions in the pipeline. Next is control hazards. They emerge from the pipeline of branches and other directions that changes the program counter. So our last topic is find whether the processor level parallelism is available in the element selected. Illustrate cache coherence and protocol used for handling memory hit or miss. So we'll consider three alternative architectures: array processor, multiprocessors, and multi-computer. An array processor comprises of an enormous number of processors that plays out similar succession of guidelines on variables arrangements of information. A vector processor is effective at executing a grouping of procedures on sets of data components. The entirety of the expansion activities are acted in a solitary, heavily pipelined adder. The handling components in an exhibit processor are not autonomous C++, since there is just one control unit in the microcontroller used. The primary memory equal framework with the different out and out CPUs in the multiprocessor. This is a framework with multi-center processor sharing a typical memory coordinated in programming. The least difficult one is to have a solitary transport with different CPUs and one memory all connected to it. In spite of the fact that multiprocessors with few processors are generally simple to fabricate, huge ones are shockingly hard to develop. The trouble is in interfacing all the processors to the memory. These frameworks are called multiprocessors. A cache hit is a state where information mentioned for handling by a part or one of the other hand application is found in the cache memory. It is a quicker method for conveying information to the processor as the cache as of now contains the mentioned information. A cache hit happens when application or programming demands information. To start with, the focal preparing unit CPU searches for the information in its nearest memory area, which is typically the essential cache. On the off chance that the mentioned information is found in the cache, it is used as a cache hit. A cache hit serves information all the more rapidly, as the information can be recovered by pursuing the cache memory. It causes execution delays by requiring the program or applications to bring information from other cache levels or the principal memory. Thank you.